Hi all, welcome back to discussion on quantum mechanics. So in this lecture, I'll be introducing Dirac notation. So this would be a very important session to all of you because hereafter we'll be using the Dirac notation to represent the vectors throughout the course. Okay, now we know that every vector has its own identity and it is independent on the coordinate system chosen. For example, in case of 3 dimension, if you consider a vector, we can visualize some specific direction for that vector, and it will have a specific length independent on the coordinate system. Whether you choose the Cartesian coordinate or spherical coordinate, the length of the vector and direction of vector will remain same. Okay, so that is true in the case of the linear vector space also, or in the Hilbert space also. A vector has its identity independent on the basis. So that is why the Dirac introduced an elegant notation to give the vectors free from the basis, to represent the vectors the free from the basis. And actually its motivation started from the inner product. Okay, so we know that if you take two vectors, psi and phi, in Hilbert space, we can introduce the inner product between them. So inner product, what usually we write as psi comma phi. And what the Dirac has done is he has replaced this notation into in new way psi phi. Okay. Now earlier this psi is called the pre-factor and this phi is called the post factor. Now this inner product in Dirac notation, this inner product is the inner product between two vectors from two different spaces. Okay, so what he has done is this we can call it as a bracket. Okay, usually we can call this as a bracket. So he has divided this into Bra and Ket. So this psi is called the Bra vector and phi is called Ket vector. Now these Bra vectors and Ket vectors are the vectors from two different spaces. This Ket vector is a vector from Ket space and the Bra vector is called the vector from the dual space. And the dual space is also known as Bra space. So that means for every vector Ket psi, for every vector in Ket space, there will be a vector, there will be its dual vector in dual space. The dual space is also called the Bra space. So if you have the vector psi in Ket space, there will be corresponding vector Bra psi in the Bra space. Okay, so this by pronunciation we call it as a Ket psi, and this we use a pronunciation Bra psi. So this introduction seems to be very simple, but it is very very handy for the algebra of quantum mechanics. So our algebra becomes very elegant, and the steps would become more easy if you use this kind of notation. So there is the power of this bracket notation. So actually the meaning of the inner product sci-fi, the inner product sci-fi, they are same. Okay, but only the notations are different. But this notation is very powerful. So that we'll understand, that we'll come to know while we are moving ahead of this course. Okay, now we can just list out the properties of the Dirac notation. So as we said, for every Ket vector psi, there will be corresponding the Bra vector psi in the Bra space. So this is the first property. For every Ket vector psi, we can identify a Bra vector psi. So this is in the Ket space. This is in Bra space. Now, if you multiply a scalar with a vector psi, plus another scalar with another vector phi, then the correspondingly in Bra space, we can write Bra psi, and we have to take the complex conjugate of the scalar plus the Bra phi, and we have to take the complex conjugate of this side scalar. In third condition, the inner product between the phi and psi, we can write, if you change the order, instead of phi psi, if you change the order, we have to take the complex conjugate. So that is already known to us. Now phi with a multiplied on psi, that is simply equal to a can be taken outside and inner product phi psi. So these are properties of scalar product. Okay, now this is not equal, this must be equal. Okay, and we can list out all other properties of the inner products, like the distributive property also we can write. So this is equal to a times phi psi 1 plus b times phi psi 2. Now, if the product is with the Bra space, so phi a comma psi is same as a star phi psi. So if you consider the distributive property, for example, a1 phi 1 plus a2 phi 2, this complete thing is in the Bra space, and in Ket space, suppose b1 psi 1 plus b2 psi 2. This can be written as 4 inner products. One is a1 star b1, the inner product between the phi 1 and psi 1, plus a1 star b2, the inner product between the phi 1 and psi 2, plus a2 star b1, the inner product between phi 2 and psi 1, plus a2 star b2, the inner product between phi 2 and psi 2. So all these conditions is based on the inner product of the vectors. Okay, now based on the inner product, we can define the norm also. So the norm of any vector psi, it is inner product psi all raised to 1 by 2. Now, if it is normalized For unit norm, the inner product with itself must be identity, so must be 1. Now we can write another thing, the orthogonality condition. So the inner product between psi phi, if it is 0, then we can say that the psi and phi are orthogonal. Orthogonality condition. If you combine the 8 and 9, we can write the orthonormality condition. So consider the ket phi I are the basis or orthonormal basis. Then the inner product phi I, phi j would be equal to delta ij. Okay, so that's all about the properties of the Dirac notation, or the writing of Dirac notation in the different context. Okay, now we can use this Dirac notation to prove the completeness, or to get the expression for the completeness property. So we have found the completeness property of the basis in the last class for the continuous basis. Okay, now consider ket phi I is a complete basis. Then any vector psi we can expand in terms of phi I. So a vector psi I can write sum over I, the expansion coefficient ci phi I. Then take the inner product with phi j. So phi j with psi would give the inner product phi j sum over I ci phi I. So this sum over I ci can be taken outside using the distributive property of the inner product. So this become inner product phi j phi I. Now this is a complete basis, and we also has to assume it is orthonormal. If it is orthonormal, then the inner product phi I phi j must be equal to delta ij. So therefore this become sum over I ci delta ij, or that will be simply equal to cj. So the expansion coefficient cj is simply phi j psi. Okay, then how can we write ci? Then our original vector psi we can write sum over I equal to 1 to n. ci we can write as inner product phi I psi inner product phi I. So this can be written as sum over I equal to 1 to n. This is just a number, this is a vector. Now we can interchange these two, there is no issue. So we can write this phi I first, then we can write the phi I psi. Okay, now just simplify this sum over I equal to 1 to n phi I times psi. Left side is psi and right side also we have a psi. Then what should be this quantity? This quantity must be equal to identity. Okay, so it's a very important thing. So sum over I equal to 1 to n phi I must be equal to identity. So this is what is called the completeness of basis. So here we have a new kind of notation. So usually we write the inner product as the first we'll write the bra vector, then ket vector. So this is what is called inner product. But here the order is different. First we have written the ket vector, then the bra vector. Now such kind of notation is called outer product. Okay, so if a basis is complete, then its sum of outer product of basis vectors must be identity. So that is what is called the completeness, or that is the condition of the completeness of basis. So if this is true, then we can expand any vector psi in terms of the basis vector I equal to 1 to n. Okay, so that is enough for the time being. And in the textbook, we can see certain other kind of things as well. For example, you can see the Schwarz inequality, a triangle inequality, etc. Okay, so all those things we'll discuss later. We required those inequalities. Particularly, we required the Schwarz inequality while discussing the uncertainty principle. Triangle inequality is not required. So that I am giving as an assignment to you. So the assignment Schwarz inequality and triangle inequality. There is nothing great in this. This is just the extension of what we have discussed for the vectors in three-dimensional vector space. Okay, so that is not very new to you. So this is enough for the time being. So we have introduced a new notation for the vectors. So now hereafter we'll be introducing this notation. This bra space notation, Ket space notation, or bra vector and Ket vector would be introduced, would be used hereafter to represent the vectors in the Hilbert space. Okay, so thanks for watching this video. So we'll come up with more interesting video in the next class.